All right, so looking at problem number one, also I apologize for the camera angle. It's propped up on a board game, but this is the best I could do. So looking at problem one, we have two nickel complexes, and the difference between them is that one nickel complex is attached to or has four trimethyl phosphite ligands, and the other nickel complex has four trimethyl phosphine ligands. And what's observed is that the dissociation constant or equilibrium constant in the dissociation of this top complex is significantly less than one, whereas the dissociation of this bottom complex is greater than one. And while the immediate approach may be to look at the bond strength between nickel and phosphorus, I actually found a better approach to be to look at the stability of the converted and one ligand taken away compound. So when you look at a complex like, or when you look at a ligand like trimethyl phosphite, you see that there's actually a very large dipole moment going away from the phosphorus. And as a result, this phosphorus as a sigma donor is actually far less electron dense than the almost nonpolar bond between the phosphorus and the methyl in the trimethylphosphine ligand. And so as a result, when you look at what they'd be converted to in dissociation, this nickel, which is now going to be a 16 electron complex with the three ligands, is going to be slightly electron deficient and thus will prefer the ligand attached to it that has a greater electron density. So to recap on what we said, because of this dipole moment between the phosphorus and the oxygen in this bond, this trimethylphosphite ligand is less electron rich and thus a worse electron donor towards this nickel. And as a result, when the nickel molecule is electron deficient, it's less stable with these trimethylphosphite ligands than it would be with the better electron donor trimethylphosphine ligands. And because of this, we see that the nickel complex with trimethylphosphine ligands has a much larger dissociation constant.